Okay, so I'm Quang Lộc Lê from UCL. Today, I'm going to present about finding real works in bit programs with incorrectness logic. This is a short work with OOPSLA, Zeus, Josh, the rest over there, and Peter O'Han. So I would like to start my presentations with the first axiom about bug catching tool at scale. So Peter O'Han said that if you are going to develop a tool to find bugs at scale, please don't spam developer with false positive. So our engagement with OpenSSL developers so that they are very, very sensitive with false positives. So our tool, we developed a tool called Process, and it found 41 bugs, and 15 of them was previously unknown. We report a bug with a fix to developers, and this one is one real bug we report. So in this box, the function prepend is the first line. It includes the malloc wrapper. The malloc wrapper will allocate the new memory and assign to the pointer ESC. And after that, it uses the memset to reset the content to 0. And because the allocation may fail, so this may cause the null pointer error at the memset. So to fix this box, we propose to check the null whether the allocation failed or not. And when we report the bug to OpenSSL, one maintainer said that this is false positive because the fmalloc, the wrapper, abort when the allocation fails. Oh, this is not the only one we received from the OpenSSL developer. So 70% of the bugs we report, they say that false positive. And we need to convince them so that why we believe that is a real bug. So for this bug, I just run the tool, trace the error, and so that actually we call the wrapper in SCP, and SCP, the wrapper will call OpenSSL malloc, that is the malloc inside OpenSSL, and it say that the wrapper, the fmalloc, the malloc, OpenSSL malloc may return null, that's the call, null pointer, nothing wrong. And to double check, we do correct search. When we find that actually in the library, there's another fmalloc in this apps. And this one actually is abort at line 14 when the allocation fails. Now we understand that the maintainer, he confused between the two fmalloc. We show our finding to the developers, and he agreed that that is a bug. But he create another pull request to match two fmalloc the same at abort when the allocation fails. Okay, you can see that the few developers are very sensitive with the false positive. Okay, so our tool in this works process, we include many nice features. And in this talk, we talk about two main features. That's the under-approximation by abstraction. And the second one is a bug reporting mechanism. So later on, I can explain what is the latent, what is the manifest error. Our tool .s is at the result is precise. Hopefully, it don't spam developer very much. And second, it's very scale. It can support it can analyze very big code around hundreds of millions lines of code and support big teams, thousands of developers in the team, and with very high velocity. So the team may commit 10,000 disks per week. And our system, our tool can support the CI reasoning. .s is based on Infer framework. So Infer is original, come from the Popo paper, and the tools can analyze the whole Linux kernel less than 30 minutes. And the team spin off a company, and the company acquired by Facebook in 2013. So the tool Infer is very successful in both academy and also in industry. But it has two limitations about the foundation, and it doesn't contain any debug mechanism. So we will show that how we address these two problems in this work. The first one about the foundations. This is about Infer is based on over-approximation, but it's used as Facebook to find bugs. And as you know, that to find bugs is usually based on under-approximation, like in simultaneous execution, clear, or simultaneous model checking, like CBMC. And for such kind of approach, usually it analyzes program, the whole programs, starting from the main function and execute the programs until it finds bugs. And the main disadvantage of the under-approximation is that when it finds a bug, the bug inside, always inside the actual program behaviors. And that's a real bug. But what is the disadvantages? So the disadvantage is, first, it's not very scale for CI. And second, it doesn't contain any memory model to support unbounded simultaneous heaps. So for Infer, it's based on some ideas about compositional reasoning. It can support, it's not necessarily start from the main function, support anywhere analysis. And with that mechanism, it can very scale, and it's based on the memory model based on separation logic. But the main disadvantage is that when it's fire box, the box may be beyond the actual program behaviors, and this may be the false positives. So we just put two approach, under approximation and over approximations together. So under approximation is not very scale but precise, and over approximations is scale but not very precise. So how we can achieve all together scalability and precision? So we may say that I want to propose the first option about let's see the under approximation analogy of Infer, or the second option is about the compositional analogy of clear or CBMC. And for memory model, we just say that we use an under approximate analogy of separation logic, that's incorrectness separation logic in the CAP paper. So our choice in this work is the first one. We propose an under-approximation analogy of Infer using incorrectness separation logic. So we go a bit more details in our proposal. So what is the compositional reasoning? So for to analyze result of the composition programs, it is defined in terms of the results of some smaller parts of programs, and we use some means, some approach to combine the analyzed result to get bigger result. So what is the part here? The part here is the procedure, the function. So for example here, we can see two contrasts. The contrast in the left-hand side, we call that the function f1 called f2, f2 called f3, and f4. And f3 is self-recursion. So to analyze the whole programs, we will start from f3 and f4. So we get some result, and we use that result to analyze f2 and so on. And what is the analysis result? That is the summary of the function. That's either under approximate specification or incorrect triple. And the means we combine the analysis results if we use under approximate by abstraction. So first, the incorrect triple. We start from the under approximate triple. So here the triple P, C, Q. P is precondition, Q is postcondition, and C is the programs. So the triple is valid if for all the states S in the postcondition, S can be reachable by execute the program C on some states in precondition. So in other words, we can say that the postcondition is under approximation of all the states starting from execute from the precondition. And for incorrectness triple, we put one more component, that is the epsilon. in the post condition. So epsilon maybe had two values. The first one, okay, to say that programs run normally. The second one is error, that some bugs happen or something like that. And our analysis, let's see the sample about the incorrect triple. So here, let's see the summary, the triple of the function free. So we say that in the free condition, if y point to some allocation heap, and if we execute the free function, so in the post condition, the heaps will be deallocated. But another example, if we say that in free condition, the memories has been deallocated already, so we end up with a double free error in the post condition. So that is error triple. And our analysis problem is that given a programs, a control flow graphs, and the specification, the summary of the atomic procedure for the malloc, pre, and all the libraries. So our tools, the process, will infer the specification of all the functions of the programs. So how it can infer the summary, the precondition and post condition? So we based on by abstraction. So we start from over approximation by abstraction. So the problem is that given A in the left hand side and the gold J in the right hand side, so the tool will infer M and F. So that A star M implies Z star F. Star here is the separating conjunction in separation logic. So after that, M will be propagated to the precondition, so that we can infer the precondition, and F will go to the post condition. For the under approximation, we swap F and M. So not similar, but we need to handle many problems. If you notice that in incorrectness logic, if we strengthen precondition, so we may have some unsound precondition. So how we get a sound result? So first, the simple solution is that we based on the frame rules. So the frame rules, but the frame rule also quite limited because we say that if we infer the F and all variables in the F have been modified from the starting until the point we infer F, we can save to control the F into precondition. It's sound. But also we need to satisfy some side condition here about the modified variables. So to make our approach more powerful, so we propose a stuck in heap memory model. So it's a bit complicated. You can look into our papers. And also we introduce a lot of other rules to handle conditional so that we can infer the strongest precondition. So please. The second one, ideas is about the Mercury Blockchain. So if you notice that actually we not analyze the whole programs, but when we can find an error triple, how we know that is a real box? So how about this example? For example, in function f here, we update the content of the memory pointed by the input to 42. So the question is that, so should we report a null pointer error here? So it's very much depend on the input. If the input S is a null, so that should be a null pointer error. But if the input is point to the memory has been allocated, so it's normal. It's not the error. So the existing approach, Infer, they just use heuristics. Infer when they can transfer the sensitive, and based on the code around the failure, they decide whether they report the bugs or not. And another tool that's using CLI, that's the compositional version of CLI. That's one best paper award of UNICEF conference. Also use heuristics, and even they ask the user annotate some annotation, something like that. It's also analyze some version of OpenSSL, less than 3% is real works. So our work, we have the error triple, OK triple, And based on the error triple, we propose a theorem to classify where the error triple is a real box. We call that manifest box. That means the box always happen with any cone to it. And the second is not the manifest box, we call that latent box. That means only some cone to the function cause the error. So we go to a bit detail by example. We back to the example I showed before in OpenSSL. So here you can see that the malloc here, the function here, the null pointer here always happen whenever the function will call. So we classify it as a manifest box inside this function. In another example, in chop-up argument here, so it's also allocates a memory at line number 6, and after that it updates the content as line number 9. But you can see that actually the allocation only happens when the input, the count values of the input equal to 0. That means only some input, this error happen, not all. So we classify as latent, and later on, if in another function, main function here, it's called the chop-up one, and it's passed the parameter with count equal to 0. So now it's become manifest because the bug always happen. And we report the bugs in the main function, not in the chop-up argument function. And that's in the theorem. So I just want to give some intuition. You don't need to understand everything. But here we have a triple P, C, Q here. And we have 4 conditions. The first condition is say that we don't need any requirement for precondition. And the last 3, number 2, number 3, and number 4, it say about the post-condition. It say that the post-condition should be satisfied and don't have any inconsistency in the post-condition so that we don't have a dash code. Okay, you can look more in our paper. The last one is about the implementation and evaluation. So Tony Hoare said that we are scientists, we seek for profession. But for engineer tasks, it's not idealistic, it's realistic. So somehow we need to balance between perfection and realistic. And when we do implementation, also inside the Infer team, always has a question. We need to choose the design between the speed and precision. So people say that, should we build a tool run very fast but dumb? Or we say that it's very precise, very smart, but slow. Which option we want? And we just look into our customer. Our customer is other developer, and what they want. Actually, they want the tool run very fast, come up the result after 2 or 3 minutes. So we choose the first one, dumb but fast, and we hope that we implement it a little bit dumb, not very dumb. But it needs to run very fast. And we have some assumption. We lost our theorem. And we say that we implement an incomplete solver to check the post condition. So we just only support equality. And also we know that we need to analyze the source code, include some third-party libraries. We don't have the source code, and it include any arbitrary feature like function pointers. Okay, so we relax the theorem. Our tool puts us 5 produce false positive. And we know that. And for evaluation, our plan, we analyze our tool in OpenSSL and 8 other open source C++ projects developed and maintained by Facebook. And to classify a box, when the tool finds a box, we classify it as a 2 box. If we can find a fish, the developer fishes. If we call it expanding, if the developer haven't accepted the fish, or we call it false positive if we couldn't find a fish from developer. And the fish rate is the number of 2 bugs over total issues found by our tool. And for the plant, we will run process and infer in each project, collect the timing and bugs found by its tool. And for precision, we compare the fixed rate. For scalability, we just compare the timing. And in this talk, we skip the last one because I don't have enough time. You can look into our paper. And we evaluate and we answer two research questions. The first hypothesis is that PoolS has better fixed rate than current Infer. The second one, PoolS find new box worth fixing in current OpenSSL. For the first one, we run in a version of OpenSSL. It's around 9,000 functions and 900,000 line of code. And we compare with older Infer. We choose this version because the older Infer, the Infer in 2015, is found 15 bugs there. It was just one reason compared to the current Infer. And the results show that PoolS found 26 issues, and 19 of them is true bugs, and 7 is false positive. The fixed rate is 33%. And Infer is found 80 issues, 39 is true bugs, and 8 of them overlap with PoolS. And 41 false positive. The fixed rate around 50%. So our tool, the fixed rate is better than Infer, around 1/2. For second hypothesis, so we just run 2 tools on current OpenSSL. That's the OpenSSL last summer. So this version, we have around 30K procedure function. And the result is that PoolS found 30 bugs, 30 issues, and 15 of them is true bugs. So the fixed rate is around 50%. So we just report the bugs. Also, how we fix this through some pull requests. So when we propose a fix, we just apply it and rerun the tool to make sure that the bugs doesn't occur anymore. And after that, we report to OpenSSL maintainer. So for Infer, it's for 116 issues, and 7 of them are true bugs, and all 7 overlap with what we found. And 40 false positive and 69 we haven't checked. It's enough for us. And the fixed rate may be from 6% to 65%. So you can see that average fixed rate of PoolS is 61%, and Infer maybe range from 23 to 60%. And at Facebook, we developed a version for company called that the PoolS is the sibling of PoolS. And the fixed rate, we improved the fixed rate of the PoolS from around 50% to 82%. That's the result of last year, the first half of last year. So I think the result can be considered is quite good. Fixed rate, also the new box. And other thing in the paper you can look in, that's how we detect the memory and also evaluation for the scalability. So for conclusion, I hope that you enjoy the talk on our tool. So we present about the PoolS, about under-approximation by abstraction, the 2 positives theorem, and so the evaluation and the experiments. So our tool find 41 bugs, 15 of them was previously unknown, and the fixed rate around 22.7, better than Infer, and it's also as scale as Infer. So if you want to learn more about Incorrectness Logic and under-approximation, or you want to reuse our work, our code to develop your tool, please attend our tutorial at POCO next year. Thank you very much for your listening.
Yeah, thank you for the talk. And we have time for questions.
Hi, thank you for the talk. In this field of research, I feel finding the bug in the loops sounds tricky and very hard to do. I wonder how this POSX deal with loop, and can POSX find many bugs in the loops or not? Yeah, thank you.
Yes, thank you for your question. Your question about how we handle the loops. Currently, we ignore the loops. We just for the loops, we just unroll it because in incorrectness logic, it's the under approximation. So it's sound to just unroll few times. So we just by default we unroll the loops around 20 times. Okay, and actually handle the loops, we have another work ongoing, and how we infer the variant of the loops and replace it, because actually the loops also very tricky problem also in company and many things, and it's very interesting problem. So, but it's this work we not do anything in the loops, just unroll it. Hopefully that's the answer to the question. Yes.
Thank you for your talk. What is the most complex bugs you guys have find in OpenSSL?
What is the most
Complex bug you guys have find in OpenSSL?
Yeah, I think in OpenSSL we found two types of bugs: the null pointer and memory leak. And actually, the null pointer errors is very simple. If you look into the symbol, it's simple like the symbol there. And we don't know why the developer they introduced it kind of, maybe they have some confusion. The code base is very large, they cannot see. But the memory list is very complicated. Some memory list the tool report, and it took me days to analyze, understand why the bugs happen. So the memory list usually is involved a lot around some bugs involved about 10 other functions, and we need to understand, analyze, and to make sure that that is the real works, something like that. Yeah. Yes.
Okay, I guess we have time for a last quick question, if there's one. Yes.
Thank you for the talk. So I didn't quite understand. Is it possible to make the solver, like, is the solver configurable? So if I don't want false positives, can I run your tool in some mode that doesn't give me false positives? With that, like?
Yes, the question is about incomplete solver. So I think you need to talk about some condition. If you just say that you don't want to relax the two positive theorem, and you say that I want to perfect tool. So first, you need to make sure that what is your input. Your input also very nice, because you know that the program maybe beyond of design programming, you have the best solver, the best input, and in input you don't have many queries feature for pointer function, and actually you can achieve that one, because for the function pointer or unknown function, actually we know that there are some involved there, and we say that we have a flash, say that an option. We say that now I don't want to report the box related to unknown function. We can remove it, but when we remove that, we remove a lot of real works. That's a problem. So in company, people just interest also 80% of its rate, because they okay, that's good enough, and we accept that our tool not a perfect one. Okay, but in your application academy, maybe we want to do something like that.
Okay, let's thank Locke again.